Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise ECE Network Analysis paper solution series. In this tutorial, we are going to solve VTU CBCS scheme network analysis questions of module 5 of June-July 2017 paper of syllabus 15 EC34. I prefer to emphasize on concepts, strategy and thinking process rather than the detailed mathematical steps. I am sure you are well equipped with required mathematical skills. Hope you will enjoy the travel. Let's go ahead. Friends, first let us solve the question to derive expression for Z parameters in terms of H parameters of a two-port network. Let me briefly explain the basic concept of two-port network parameters. Two-port network parameters are defined parameters in terms of input and output quantities under specified conditions. Consider the block diagram of a two-port network shown in figure. V1 and I1 are the voltage and current quantities at the input port. V2 and I2 are the voltage current quantities at the output port. Friends, two-port network parameters are considered to be inside a black box. They are not accessible for the user. But what are accessible for the user are only the input and output terminal quantities. In this question, we are required to derive expression of Z parameters in terms of H parameters, meaning we know H parameters and using them we need to derive equations for Z parameters. We know that two equations which completely describe the behavior of two-port network in terms of Z parameters are Z11I1 plus Z12I2 is equal to V1, let it be equation 1, and Z21I1 plus Z22I2 is equal to V2, let it be equation 2. Similarly, the two equations in terms of H parameters are H11I1 plus H12V2 is equal to V1, let it be equation 3, and H21I1 plus H22V2 is equal to I2, let it be equation 4. Friends, you should learn to remember and reproduce these equations correctly because the whole derivation will be wrong if these equations are not correct. So, friends, these equations are reproduced here for your convenience. The strategy of obtaining the expressions will be consider the two equations of the parameter you know that are here H parameters. The first step will be using equation 4 transform equation 3 such that it is analogous to the input equation 1. Let the transformed equation be equation 5. Then compare the coefficients of I1 and I2 of both equations 1 and 5 and find Z11 and Z12. Observe equation 1. It relates the terminal quantities I1, I2 and V1. Similarly, observe equation 3. It relates I1, V2 and V1. Friends, for equation 1 and equation 5 to be analogous, we have to eliminate V2 in equation 3 using equation 4. So, consider the output equation 4. Rearranging it, we get V2 is equal to 1 divided by S22 into I2 minus S21 divided by S22 into I1. Substituting this value of V2 in equation 3 and using simple algebra, we get to the equation H11 minus H21 divided by H22 into I1 plus H12 divided by H22 into I2 is equal to V1. Friends, By rearranging and solving the equation we obtained, we get delta H divided by H22 into I1 plus H12 divided by H22 into I2 is equal to V1. Let it be equation 5. By comparing the coefficients of I1 and I2 of both equations 1 and 5, we get Z11 is equal to delta H divided by H22 and Z12 is equal to H12 divided by H22. Now, to get another two expressions for Z21 and Z22, we have to follow the same process of using equation 2 and equation 4. What we have to do is, using equation 3, transform equation 4 so that it is analogous to equation 2. That's all. So, observe equation 2. It relates I1, I2 and V2. Similarly, equation 4 relates I1, V2 and I2. You see that both equations relate to the same terminal quantities, meaning we have to just rearrange equation 4 to be analogous to equation 2, that's all. So, rearranging equation 4, we get minus H21 divided by H22 into I1 plus 1 upon S22 into I2 is equal to V2. Let it be equation 6. By comparing the coefficients of equation 2 and equation 6, we get Z21 is equal to minus S21 divided by S22 and Z22 is equal to 1 divided by H22. So friends, the final expressions we obtained are represented in determinant form as shown. Is it not simple, friends? Friends, next we shall solve the problem on two-port networks to find ABCD parameters. First, let me discuss the strategy and thinking process. Observe the given network. It is a simple pi network, but the network elements are given as 1 ohm and 1 farad. Note that the frequency is not known. So, under such circumstances, we need to transform the entire network into S domain using Laplace transforms. We know that L of V of t is equal to V of S, L of I of t is equal to I of S, and L of R of t is equal to R, and transform of capacitance in impedance form is 1 upon S. Using these transforms, the transformed circuit is shown in figure. Note that all the circuit elements are transformed into their equivalent impedance form. Next, to find ABCD parameters, we know that the two equations that describe the complete behavior of the network in terms of ABCD parameters are V1 is equal to AV2 minus BI2, let it be equation 1, and I1 is equal to CV2 minus DI2, let it be equation 2, where A is equal to V1 divided by V2 when I2 is equal to 0 and C is equal to I1 divided by V2 when I2 is equal to 0. So, to find these two parameters A and C, we need to force I2 is equal to 0. Hence, forcing I2 is equal to 0, the circuit drawn is shown in figure. Friends, observe the network. Hope you recognize that voltage across the first capacitor is V1 of S and voltage across the second capacitor is V2 of S. So, let I3 of S and I4 of S be the currents through the first and second capacitor respectively. You find that I3 of S is equal to V1 of S divided by 1 upon S, which will give us I3 of S is equal to V1 of S into S. Similarly, I4 of S is equal to V2 of S divided by 1 upon S, which will give us I4 of S is equal to V2 of S into S. But V1 of S is equal to V2 of S plus 1 into I4 of S. By substituting for I4 of S and solving, we get V1 of S is equal to V2 of S into bracket S plus 1. But we know A is equal to V1 by V2 when I2 is equal to 0, or A is equal to V1 of S divided by V2 of S, which will give us A is equal to S plus 1. Next, to find C, observe the network. You find that I1 of S is equal to I3 of S plus I4 of S. Note that I2 of S is equal to 0. By substituting for I3 of S and I4 of S and solving, we get I1 of S is equal to S into bracket V1 of S plus V2 of S. But C is equal to I1 divided by V2 when I2 is equal to 0, or C is equal to I1 of S divided by V2 of S. So, by substituting the values and solving, we get C is equal to S into bracket S plus 2. Next, to find the parameters B and D from equation 1 and 2, we find that minus B is equal to V1 divided by I2 when V2 is equal to 0, and minus D is equal to I1 divided by I2 when V2 is equal to 0. So, we need to force V2 is equal to 0. Then, by forcing V2 is equal to 0, the circuit drawn is shown in figure. Now friends, keenly observe, second capacitor of 1 upon S is short circuited, so we can remove it from the network. Further, you observe that V1 of S appears across the first capacitor of 1 upon S as well as across 1 ohm resistance. So, minus I2 of S is equal to V1 of S divided by 1, which will give us V1 of S, or I2 of S is equal to minus V1 of S. That is simple. But we know minus B is equal to V1 divided by I2 when V2 is equal to 0, or minus B is equal to V1 of S divided by I2 of S, which is equal to V1 of S divided by minus V1 of S, which will give us minus B is equal to minus 1 or B is equal to 1. Similarly, to find D, we have I phi of S is equal to V1 of S divided by 1 upon S, which will give us I phi of S is equal to V1 of S into S, and I1 of S is equal to I phi of S minus I2 of S. Note this. By substituting the values and solving, we get I1 of S is equal to V1 of S into bracket S plus 1. But we know minus D is equal to I1 divided by I2 when V2 is equal to 0, or minus D is equal to I1 of S divided by I2 of S. By substituting the values and solving, we get D is equal to S plus 1. So, ABCD parameters obtained are represented in determinant form as shown. Friends, let us solve another interesting problem to find Y parameters of the circuit shown in figure. We know the two equations that completely describe the behavior of the network in terms of Y parameters are y11 V1 plus y12 V2 is equal to I1, let it be equation 1. y21 V1 plus y22 V2 is equal to I2, let it be equation 2, where y11 is equal to I1 upon V1 when V2 is equal to 0, and y21 is equal to I2 upon V1 when V2 is equal to 0. So, to find y11 and y21, we need to force V2 is equal to 0. By forcing V2 is equal to 0, the circuit drawn is shown in figure. Observe that the network has turned out to be a 3-node network with 2 unknown node voltages V1 and V2 as shown. Of course, V2 is equal to 0, we know. So, by writing the nodal equation for node V1, we get minus I1 plus V1 by 1 plus V1 minus V2 by 2 is equal to 0. By substituting V2 is equal to 0 and solving it, we get I1 is equal to 3 divided by 2 V1. But we know Y11 is equal to I1 divided by V1, and hence Y11 we get is equal to 1.5 mho. Similarly, by writing the nodal equation for node V2, we get V2 minus V1 divided by 2 plus V2 divided by 2 plus 3I1 minus I2 is equal to 0. By substituting V2 is equal to 0 and solving it, we get I2 is equal to 4V1. But Y21 is equal to I2 divided by V1, which will give us 4V1 divided by V1, and hence Y21 is equal to 4 mho. Next, to find Y12 and Y22 using equation 1 and 2, we see that Y12 is equal to I1 by V2 when V1 is equal to 0, and Y22 is equal to I2 divided by V2 when V1 is equal to 0. So, to find these two parameters, we need to force V1 is equal to 0. The circuit drawn by forcing V1 is equal to 0 is shown in figure. Note, resistance of 1 ohm is short circuited and hence we can remove it. By doing so, you find that the circuit is reduced to 2-node network with only one unknown node voltage V2. So, by keenly observing the network, we find that minus I1 is equal to V2 divided by 2, but Y12 is equal to I1 divided by V2, and hence we get Y12 is equal to minus 0.5 mho. It is so simple, isn't it? To find Y22, by writing the nodal equation for node V2, we get V2 divided by 2 plus V2 divided by 2 plus 3I1 minus I2 is equal to 0. But I1 is equal to minus V2 divided by 2. So, by substituting and solving, we get I2 is equal to minus 0.5 V2. Therefore, Y22 is equal to I2 divided by V2 we know, and by substituting we get Y22 is equal to minus 0.5 mho. Hence, Y parameters obtained are represented in determinant form as shown. Is it not simple, friends? Friends, finally, let us solve the question to derive the expressions for H parameters in terms of Y parameters. The question is straightforward. We know that the two equations that completely describe the behavior of two-port network in terms of H parameters are H11I1 plus H12V2 is equal to V1. Let it be equation 1. And H21I1 plus H22V2 is equal to I2, let it be equation 2. Similarly, in terms of Y parameters, we have Y11V1 plus Y12V2 is equal to I1, let it be equation 3, and Y21V1 plus Y22V2 is equal to I2, let it be equation 4. Hope you understand that we know Y parameters, and using equation 3 and 4, we have to derive the required relations. So, the strategy will be using equation 4, transform equation 3 such that it will be analogous to equation 1. So, observe equation 1. It relates to the terminal quantities I1, V2 and V1. Similarly, Observe equation 3. It relates V1, V2 and I1. You see that both equations relate the same terminal quantities. So, we have to just rearrange equation 3 such that it is exactly analogous to equation 1. By rearranging equation 3, we get 1 upon y11 into I1 minus y12 divided by y11 into V2 is equal to V1. Let it be equation 5. Comparing the coefficients of I1 and V2 of both equations, we get H11 is equal to 1 upon Y11 and H12 is equal to minus Y12 divided by Y11. To find expressions for H21 and H22, we have to use equation 3 and transform equation 4 to be analogous with equation 2. So, observe equation 2. It relates the terminal quantities I1, V2 and I2. Similarly, observe equation 4. It relates V1, V2 and I2. You see that the terminal quantity V1 is to be eliminated from equation 4 using equation 3. So, using equation 3 and rearranging it, we get V1 is equal to 1 upon Y11 into I1 minus Y12 divided by Y11 into V2. Substituting this value of E1 in equation 4 and rearranging it using simple algebra, we get y21 upon y11 into I1 plus delta y upon y11 into V2 is equal to I2. Let it be equation 6. By comparing the coefficients of I1 and V2 of both equations, we get H21 is equal to y21 upon y11 and S22 is equal to delta y by y11. The expressions obtained are represented in the form of determinants as shown. Is it not simple, friends? Friends, after going through this tutorial, I hope you are convinced that the two equations that describe the complete behavior of the two-port network are the beginning of any circuit solving on two-port networks. The four different two-port networks are Z, Y, H and T or ABCD parameters. Remembering, recalling and reproducing the relevant pair of equations correctly is an important step. So, I suggest you find your own strategy using memorizing techniques such as connect and link, associate, repeat or keep writing until you memorize by heart. Further, you might have noticed that in some problems we have used basic circuit solving technique and in some other a node voltage method and so on. It's not necessary that we have to use the same technique for all problems. You will have to think and decide what method of circuit solving will give fast and correct results. You have to develop this skill by solving the same problem using different methods. Friends, I am sure this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.